Okay, welcome back. Let's talk about synthesis in relation to aromatic compounds. So the first thing I want to show you is an overview of all the reactions we've talked about thus far in relation to substitutions at the aromatic ring. Starting with benzene itself, you could undergo halogenation via substitution using the dihalogen such as dichlorine or dibromine in the presence of iron 3 halide. You can also undergo sulfonation by treating the benzene ring with oleum, a mixture of sulfur trioxide in concentrated sulfuric acid. And out of all the reactions, is the only one that actually is part of an equilibrium, which will allow you to remove, if you want to, the sulfonic acid group just by treating it with dilute sulfuric acid. Additionally, you can carry out alkylation reactions using an alkyl halide and aluminum chloride. Now, these reactions have two potential drawbacks. The first one is that carbocation rearrangement can occur before the aromatic substitution happens. And two, once you install the alkyl group, because it is an electron donating group, it can activate the ring to do further alkylation. So it's not uncommon in this situation to end up with dialkyls or even trialkyl derivatives. Now, on the other hand, the acylation reactions don't suffer from rearrangements. So you can definitely install, if you want, a primary or secondary alkyl directed to the benzene ring, even in the presence of neighboring tertiary carbons, because they don't really have a problem with arrangement as a result of the oxygen getting involved in the resonance structure. Now, the good thing about them is that because they are deactivating groups, they don't undergo multiple acylations. And the other thing is that you can easily remove the oxo group by treating this thing with tin in HCl. So it's actually a very, very nice way of carrying out that reaction. All right, so another reaction that's important to keep in mind, because this will lead us to an avalanche of other reactions, is the nitration of the benzene ring, which is done with 1 part nitric acid, 1 part sulfuric acid, both of them highly concentrated. This will give you a nitro substituent on the benzene ring. And the nitro substituent is electron withdrawing. It's a strong electron withdrawing group as well, but it can be turned into a strong activating group if you reduce the nitro group with tin, HCl at low temperature. You could also do this with iron and HCl. They both basically do the same overall process. They turn the NO2 group into an NH2 group, and this is a strong activating group. So you can change the nature of the benzene ring as an electrophilic substitution reaction is concerned just by making that particular change on the substituent itself. Now, the aniline group, yes, can enhance the electrophilic substitution at the benzene ring, but it can also be a reactive substituent, specifically if you treat it with sodium nitrite in HCl at low temperature. You can generate the diazonium salt, which becomes the big entry point to installing a variety of substituents. You can install halogens such as chloro, bromo, but you could also install the iodo and the cyano substituents by using copper 1 salts of the corresponding anion. Additionally, you could make the phenol derivatives simply by treating the diazonium salt with water and mild heating. You can install the fluoro substituent with tetrafluoroboric acid and heat. And although I'm not showing that in here, if you treat the diazonium salt with tetrafluoroboric acid in the presence of sodium nitrite and copper, you can reinstall the nitro group back in that position. And likewise, if you treat the diazonium salt with hypophosphorous acid, you can reinstall the hydrogen substituent where the diazonium salt was located. So basically, keeping all of this in mind is going to be important, because we will make use of the activating and deactivating nature of the various groups to determine and exploit activation at the orthoparasites or the metacytes, depending on what it is that we're trying to synthesize. So I'm going to show you a series of examples to kind of emphasize that idea. So let's say, for instance, that we have benzene as a starting material, but what we want to make is 1-bromo 2-propyl benzene. Well, in this case, we have to consider a number of things. First of all, as you look at the molecular structure of the target molecule, one thing that you should notice for the alkyl in particular is that the position directly attached to the benzene ring happens to be a primary carbon, and that carbon itself is next to a secondary carbon within the alkyl chain. So what that should tell us is that probably a direct alkylation is not going to be the way to go. But before I get there, another thing to also notice is that the position between the bromo group and the propyl group are ortho to each other. So we're going to need an ortho-directing group for that to happen. But here's the deal. When you want something to end up in the ortho position, you have to use a group that activates both the ortho and the para positions. And as you can see right here, we have nothing in the para position in respect to the alkyl group. So we're going to need to prevent that para substitution from happening. And if we don't do something to prevent your substituent attaching to the para position, you better be sure that you will get substitution at the para position and the ortho position as well. In other words, you'll end up with a mixture. So as far as the strategy goes, being that we want to have a lower substituted carbon directly attached to the benzene ring compared to one that's more substituted down chain, means that we better be doing this via an acylation, a Friedel-Crafts acylation reaction, as opposed to an alkylation. The second thing is that once we get the acylation, obviously we don't want the carbonyl group left over, so we're going to have to get rid of it. So we're going to have to reduce it to end up with the proper alkyl. And then the last thing is that to ensure that the pair position never gets touched, that's where we're going to use the sulfonyl group as a blocking group, which after the fact we can remove just by using dilute sulfuric acid. So the retrosynthesis in relation to this molecule will be as follows. This is the targeted molecule. How we install the substituents, well, you could go based on the idea that, well, the bromo group is a weakly deactivator group, but it does allow for ortho-para substitution. Now, the alkyl group is a weakly activating group and also promotes ortho and para substitutions. And since the two of them are ortho to each other, it would be a little bit more beneficial to you to make use of the alkyl as the directing group. So one thing that you might want to do is before you get to this final thing, you will have to have the sulfonic acid group in the para position to block it. So basically, this sulfonic acid group will have to be present before we add the bromine. So you will pretty much have your alkyl first, then you install the sulfonic acid, which it's very likely to go in the para position. You might get some on the ortho, so you might have to do a little bit of separation and a little bit of purification. But once you have the proper molecule, with the sulfonic acid group on the para position in respect to the alkyl chain, then you can do your bromination to end up in the ortho position. And after you do that, you can react this molecule in dilute sulfuric acid to remove the sulfonic acid group from the ring, yielding the final molecule. Now, as far as generating this thing, it would just be the alkyl, the propyl benzene derivative, reacting with oleum to give you the sulfonic acid derivative. And the alkyl derivative itself can be synthesized from the acylated derivative, which in order to carry out this reaction, you will have to treat this with zinc in HCl. And then the acylation can happen itself directly from the benzene ring by reacting the benzene ring with the acyl chloride derivative in the presence of aluminum chloride, or alternatively iron 3 chloride. All right, so that would be kind of a way to kind of think of this. And of course, you'll be on the hook for writing down all the reaction conditions that will lead you to each of the steps as you go through the synthesis. All right, now let me show you another example. Now in this example, I want to make para-chlorofluorobenzene out of benzene itself. So as far as the structural analysis, just from the name alone, I kind of gave it away. But these things are going to be paired to each other. And the floral group, out of all the things we've talked about, the only way that you know how to put a floral group on benzene is via a diazotization. So we're going to have no choice but to do a diazotization just to get the fluorine installed into the benzene ring. The second thing, which I've already mentioned, is that the two groups are paired to each other, so we need to avoid orthosubstitution in the synthesis of this molecule. So one way that we can kind of go about it, since we're going to be doing a diazotization, is to use a moderating activating group, which is basically the acylated version of the amine. So basically, instead of amine, we'll use an amide. And we're going to go in more detail about this reaction, but you could remove the amide just by reacting this with acidic aqueous solution and a little bit of heat. All right, so here's how it will go. To generate parachlorofluorobenzene, you would want to basically precede this from the diazotization reaction. That's the only way to install the fluoro group at that position. And then the diazonium reagent itself is going to have to be made from the aniline derivative. Notice that in all of them, the chloro group is there because that's going to be one of the earlier steps in the retrosynthesis. Now, the amino group can be formed from the acylated version, which is the amide. And this is a group that is moderate in terms of its activating power. So what that means is that we could actually start from the amide derivative of this benzene ring and do the chlorination. And we could pretty efficiently end up with the para-substituted product. Now here you will probably get some of the ortho and you will probably have to do a purification via column chromatography. But that aside, you can generate the para-chloro derivative relatively well with this reactant. And by the way, the acylation of the nitrogen is done such that you don't undergo multiple chlorinations. Because if this was straight out NH2, you will very likely end up with 3 chlorines at all the ortho and para positions. So this is one way to kind of, cool it down a bit and end up with only one substitution. All right, now the amide derivative can be formed from aniline itself just by reacting aniline with acetyl chloride or acyl chloride. And the aniline itself can be made from nitrobenzene just by reacting nitrobenzene with tin in HCl. And nitrobenzene can be made from benzene directly upon reacting benzene with nitric acid and sulfuric acid. So that would be a route to kind of consider. All right, and I'll show you one more example of how this works out. Let's say that we want to make the following molecule right here, basically menthol, or a derivative of menthol, actually. So the things to consider are the following, right? So we have directly from benzene, we have to consider that we have an isopropyl substituent, a methyl substituent, and then we have the alcohol substituent, right? So the methyl substituent is less bulky, and because you don't have any other sources of carbon, you could do this directly via alkylation. You could still do it via acylation if you want to, but alkylation is an option because rearrangements are not going to be really happening. You only have one carbon. Now, the hydroxyl substituent, this we can only do via diazotization. There's no other route that you know of in this class that can install that OH group. And then the isopropyl is the bulkier group. So you might want to keep this handy because the bulkier the group becomes, the harder it's going to be for you to install substituents on the ortho position of the bulkier group. So we might actually make use of that to prevent ortho substitutions in respect to the isopropyl, and therefore perhaps use the isopropyl as one of the starting points on the synthesis. So as far as the strategy goes, we could definitely do installation of the methyl group via acylation to avoid polyalkylation if we want to start with that to begin with. There's a different route that we could also use, but we could try to do that. And we could apply the bulkiness of the isopropyl group to ensure that the next substitution happens para to the methyl group as opposed to ortho. All right, and then the last substitution has to occur in the less bulky ortho site. All right, so between the ortho isopropyl and the ortho methyl, the ortho methyl seems like a more likely place to end up with a substitution. And remember, both the isopropyl and the methyl group are ortho para directors. So the ortho position of the methyl is activated, the ortho position of the isopropyl is also activated, but the sterics will kick in to help you out somewhat there. All right, so as far as the final molecule, we can install that OH group from a diazotization reaction. So the diazonium salt will be the precursor to the alcohol. And at that point, it's just simply reacting this molecule with water and then heating. The diazonium salt is itself formed from the aniline derivative just by reacting aniline with sodium nitrite and HCl at 0 degrees Celsius. The aniline can be formed from the nitro group just by treating the nitro group with tin in the presence of HCl. And the nitro group can be installed from the isopropyl methyl derivative via nitration with nitric acid and sulfuric acid. And here we're basically allowing the activation to happen at the ortho position next to the methyl group because it's the one that has the least steric bulk associated with it. All right, so here, making the isopropyl methyl derivative, we can make that from the toluene derivative by alkylating toluene with isopropyl chloride. And because of the bulkiness of isopropyl, it is very likely that you're going to generate almost exclusively the para substitution as opposed to the ortho substitution if you start from toluene. And then, as I mentioned at the very beginning, we install the methyl group via an acylation reaction and then remove the oxo group with zinc and HCl. And then the acyl group itself can be installed via the Friedel-Crafts acylation reaction, right? So this will be, one that you really have to think about because we're talking about a total of 8 steps just to get to the final molecule. But generally speaking, these are the things that you need to consider. Where is the substitution going to end up based on the substitutions that are already present on the ring? And 2, is your group electron withdrawing, electron donating? Because that's going to affect whether or not you can carry out certain reactions or not. So anyway, with all these examples, we'll stop the video right here. And in the next one, we'll talk about benzene reactions. Okay, see you on the next one. Bye-bye.